So the first thing you always write in there, first thing you want to write in is your given statement. The 2x minus 1 is 7. Okay? What did you do next? Add prop equal. I like it. Simplify. Good, good. Yes, ma'am. Anytime. What's that? Yep, divide prop equal. Now, sorry. Now, when you're doing these things, simplify is usually in the middle. When you're doing the algebra, the end is usually just solve. Okay. When you simplify, that's when you did some math. Remember how we did that last week where we had the distributive property, and then when you rewrote it, you just said you used the distributive property. You can have multiple simplifies. You're usually only going to have one solve. This stuff was pretty simple. What we're doing today, though, is ever so slightly different. We're going to still be able to use this idea of where the math is coming from. But what we have to look at are what are called congruent figures and what are called congruency statements. We've used the term congruent and congruent figures a lot. What did congruent mean? Do you remember? You said equal. What do you mean the same? You're very close. I'm trying to see if I can get you to say the last bit. Same amount, same value. Okay. So what the difference here between we call congruent versus equal. Congruency deals with things of equal measurement. Okay. Things with equal measure. Two angles that measure the same degrees. They're both 17 degrees. That means those two angles are the same measure. That means those angles would be congruent. When things are equal, that's kind of like solving an equation. X equals 2. All right. It denotes what a value is versus congruency is a measurement. It's kind of weird, but does that make a little bit of sense? It's one of those things. Congruency statements are generally used with letters. Equality is usually with algebra. Okay? So think of things of equal measure. So what we're going to do today is we'll do something similar or something simple like this. So we have triangle A, B, and C, or ABC. When I say that I have triangle ABC, what do the letters A, B, and C represent on the triangle? The points. Points where the angles are created, those are called vertices. You guys remember that? Okay. Do we know what this triangle looks like? It can be any triangle I want, right? Okay, so if I draw a triangle, I get that, right? In any order. Does it matter the order? I can pick any vertex to start with and write it. Just put it in the order of the letters, just the way that it's written. Now, when you guys label angles, give me an example of an angle in here. Like angle A. It does. I see where you're going with that, but what I'm saying is if I look at this diagram, and if I say angle A, that's the exact same thing as saying angle BAC, isn't it? It's the same thing as saying angle CAB as well. Whenever I have only one possible vertex, in this case angle A, I can use one letter. I don't have to use 3 letters. All right. The minute that this happens, if this ever has another spot going here, I can no longer call that angle A. because there are, let's see, 1, 2, 3 different angles that it could be. Does that make sense? Right, because that angle is shared by a bunch of different sides and stuff. So for our purposes, if we're dealing with triangles, or even if we're dealing with polygons with just singular vertices, and you'll be able to see that with a lot of diagrams, it's perfectly fine just to say that you have angle A. You all right with that? What are the other two angles we have? Okay, angles A, B, and C. All right, give me a side line. What was the side length, guys? BA? Could it be BA or AB? Does it matter? No. You know what? BC and CA. I was kind of leading into what I was doing there. You said BA at first, but I wrote AB. The next one went BC, then the next one CA. See, I'm just going around the picture. If you went BA, could you have said AC and then CB if you wanted to? Any one of those is fine. When you're dealing with segments, from here to the fan is the same distance from the fan to here. It doesn't matter which way you're going, because that distance is always positive. It's just direction. Direction doesn't matter. Direction is what matters. Okay? So triangles have 3 angles, 3 sides, and so on and so on. No big deal, right? You guys have all known this forever. But what the new stuff is going to be is when I take these values, move this out of the way for a second, and I put in what's called a congruency statement. What does that say? Okay. That says that triangle ABC is congruent to triangle XY. Oops. Is congruent to triangle XYZ. Now, in order for things to be congruent, they have to have equal measure, right? They have to have correspondence. They have to match. If you look at just the letters, what's the first letter in both triangles? X and A. Those two letters correspond to one another. They're in the same position in the lettering. Remember when we did corresponding angles with parallel lines? When we said corresponding angles with parallel lines, there were angles that were in the same position between the two lines. We knew that when those lines were parallel, we knew that those angles were then, in fact, congruent. So what happens here is that you get that same sort of a thing. And I hate to keep using the word correspondence, but if you follow the letters, it will always tell you what parts match with what. The idea of using this, what's called a congruency statement, will allow us to say, hey, angle A has to match up with angle X. Angle B has to match up with angle Y. Everybody see where I'm going with that? As these things match one another, all I don't even have to look at the diagram. I look at the statement. A lot of times it's all we're going to need to have to do. Learn to read the congruency statement. The congruency statement puts letters in a specific order. That means that when you make angles out of those letters, or you make segments out of those letters, those are the corresponding parts that will always be congruent. Okay. So if I mark up angle A, angle X, angle B, angle Y. Oops, move this up a bit here. Angle C has to then match with Z. And if I use 3 here, I use 3 here. Okay. Exact same thing goes for segments. The exact same thing. It just depends on how the lettering is written. Okay. AB are the first 2 letters. What are the first 2 letters of the other one? XY. That means they correspond to one another. So AB has to be congruent to XY. Also, if you start looking at the tick marks on the diagram, angle A has 1 tick mark, angle B has 2 tick marks. 1 and 2. The segment between them has to be the same because they match up with the tick marks. So AB would be congruent. XY. Hey, what? I don't want to deal with you. You trust me opening the door when you put your face in front of it. Right there. So ugly. Takes one to know, Mike. You're welcome. You too. See you, Leon. That's what we do to each other. We yell at each other and make fun of each other. It's not being a bully. Does it cancel it out then? Well, wait. Did 2 negatives make a positive? No, 2 rights don't make a right. But 3 lefts do. No, they don't. Oh my God. Stand up. Stand up. Turn left. Turn left all the way again. Turn left again. We'll wait.
That's 180. What? Oh wait, no,
No, it wasn't. It wasn't even that. Stand up again.
No, I don't want to stand up again. You do it. I'm so confused.
Stand up. Everybody stand up. All right. Now, face forward. Are you too cool for this? Come on now. If you turn left 90 degrees, okay? Turn left 90 degrees again. Turn left 90 degrees again. Now you turn right.
What?
Look at your face. It's just priceless. No answer, man. So, ladies and gentlemen, there's a state, like one of the United States, one of the 50-50s, that's not too far away from here called Michigan. It's that way. Okay? The state of Michigan. That way straight east. Okay. Anyway, in Michigan, there are many places you can't make left-hand turns at many intersections in Michigan. They have medians throughout most of the things to avoid people pulling in. It's a safety thing. If you think about it, most accidents are caused when you cross over lines of traffic. Okay? So if you're turning left, there's oncoming traffic coming towards you. That's where you get most of your accidents. So in Michigan, they don't have left-hand, they don't do left-hand turns. You are forced to make right-hand turns to get to places.
What?
Seriously. Have you not, when was the last time you guys drove down 88 towards Naperville? You know what I'm talking about, like I'm off 59 right there?
I was just on 59 on Saturday.
They have the flyover bridge there now. You guys know what I'm talking about? Have you seen that thing? So you've got 88 and 59. Instead of going north, you're actually going north on the southbound lane and cut over. That way you don't have to cross over traffic. Okay? Yeah. That way, because normally you would go into the right-hand lane and continue up north if you're going north. Let's say you're going to Topgolf. But you have to pull into what would technically be the southbound lane, the left-hand side. That way you're never crossing over traffic. It's a safety. That way traffic can flow faster. But anyway, I digress. Yes, 3 lefts make a right, and 3 rights make a.
Just do that again.
All right. Anyway, back to this. BC has to match up with what 2 letters in the other one? YZ. And then the last one was, it would be ZX. Here's the thing. CA, when we wrote it out as segment CA, I went with the last letter to the first letter. Is it the same thing as AC? Now, but here's the thing. When they write it as CA, that means you have to make the letters match the other. Go from the last to the first. That's why we say ZX. Even though XZ is the same thing, by putting it the letter-wise, that is, it's the proper way to do it, okay? Following the patterns of the letters, all right? Congruency statements. Yeah, lack of better terms. So these congruency statements allow us to do a whole bunch of junk. They're going to let us do things like this. So, trying to blow something up here. It says shape DEFG is congruent to S, P, Q, and R. One of the things why we do it this way, one of the reasons why we always want to look at the lettering is the lettering won't lie. The lettering won't mess this up. The lettering tells you what has to match with what. Don't look at a diagram and just assume you're going to figure it out. Because as we all know, there is no what in math? Right. So, well, that means you have to say it louder to make it feel. What? All right. This is turning into one of those days that you cannot tell. All right, so this tells you that angle D has to match with angle S. Just S. Okay. So if angle D is 102, what does angle S have to match? 102. Okay. This is how this stuff matches itself together. Right. Because you're following the letter pattern. Angle E has to match with angle P. Well, I have nothing here, which means I have nothing here. That's fine. Let's put a tick mark. I don't know what it is. I don't need to figure that out right now. Angle F has to match with angle Q. Well, F is 68, which means Q is 68. And then lastly, G and R, 84 up here. All right, that helps me with my with my angles. Side lengths, on the other hand, I have side length DE. DE are the first 2 letters of the first statement. That means it has to correspond to what 2 letters of the second one? SP, good. That's the idea of looking and reading your statement to understand that even though that 2x minus 4 is on the top, it doesn't necessarily mean it corresponds to the value of the other diagonal. Okay? That's where you guys will mess up, because this has to equal 12. Okay? So you do the algebra. Was it 2x minus 4 was 12, I think? Okay. You're right. What do you do first? Add the 4. And then divide by 2, what do you get? So I gave you your value of x at 8. The other one was 6y plus x is 68. Last time I checked, I can't solve for two variables at the same time. What do I do with the x, though? What do I know x is? What do I put it in? No. Yeah. What do we know? What do we know that x is? 8. It's just, we're solving for the value of x, and sometimes you have to use it again. But remember, x doesn't represent an angle, it doesn't represent a side, it just represents some value of x. That value of x just happens to be in two spots. That's all. What does y have to be? You can probably look at it and figure it out. 10. 6 times what plus 8 is 68? Well, it has to be 10. Okay? You will reuse things from time to time. That's all. Yeah, sometimes you have to do it, sometimes you don't. It just depends on the problem. I just wanted to show you something weird instead of one of the really, really easy ones right off the bat. We will. Okay. Now, the next thing that comes back with this is the idea of how you work with a diagram. And one of the things I want to do is talk about a progression. Grab your progression sheet. If you didn't get one or you need one, I have a couple of spares in the back. But we had talked about this in the past, that there are certain things that we'll be able to infer. We're not using them right now. Yes, ma'am. It doesn't matter which way you go with it. It really doesn't. Whatever way you want. Yeah. And again, this is one of those things that, as we do these progressions, these are the tips and tricks and things that you're going to be able to use. Bless you. That when we get into proofs and things. Now, last week we talked about what you can do with what's called an inference. Things that you can take from a diagram, information you can get. I think one of the things we talked about last week was a linear pair. That was one of the things we were able to assume from looking at a diagram. That's a legal thing to do. Now, when we do this one, this is something I would just put an asterisk by. It's not a true if-then statement. It's just, hey, knucklehead, look for vertical angles. Because what do you know about vertical angles? They equal each other, they're congruent. Okay? So from a diagram, if I ever see vertical angles, I can mark them as congruent. Now, when two lines intersect, we know that both that set of angles would be congruent and this set of angles would be congruent. Everybody okay with that? Those two sets aren't necessarily congruent to each other. They're just two sets of congruent angles. So in my proof stuff, as I'm going through, this would not be a given statement. This would not be like a definition that you can use like an if-then off of. But this is something that you're allowed to write down if you see it in a diagram. Here's what you would write. I would write angle ABC is congruent to angle XBY. The reason that I can do that is because we know, by definition, vertical angles are congruent. And that's what you would put in your progression sheet. Just a little example of what it would look like. Because as we get further along, we start talking about congruent. How do you show that things are congruent? Well, today we're going to talk about, in order to show that something is congruent, all corresponding parts have to be congruent. All the sides have to be congruent. All the angles have to be congruent. We don't know how to do anything except for noticing where vertical angles occur and how to switch from congruency to equality. So there's not a lot of proof to this. It's just what can you take from a diagram? Okay. And this is one of the things. Could I write out the other angles if I wanted to? A, B, X, C, B, Y if I wanted? And why can't I just say angle B? Because what? It's a vertex. It happens to be a multiple, it has multiple vertices. It's a vertex for multiple angles. Okay. If you were in a, and I'm going to get to an example of how this would go if we were doing a proof with it. It's just one of those things that if you notice that you have vertical angles, you can say. Okay? But you have to say that they're congruent before you use it. Right? For example, if I go to a picture like this, and just pull this picture separate for a second. I wanted to pull this together, and I wanted to say, show I want to show that triangles ABC and triangles EDC are congruent to one another. How many angles are in a triangle? 3. How many sides are in a triangle? 3. That means I'd have to show that all 3 sides congruent and are all 3 angles congruent. Is there enough information on here to show that those corresponding 3 angles, those corresponding 3 sides are congruent?
Yes.
Okay. How? I got the tick marks, okay? So right now I know that according to my diagram, angle A corresponds to which angle? E. They both have 1 tick mark. All right. Angle B, because the tick marks, okay. AB, is it ED? Okay. Okay. Now what? BC. DC. You gotta go DC. You started out in. So you gotta go out in. Good. We know those are all congruent because they all have equal measure. I'm missing an angle though. I can't say angle C. So if I use my letters, I have to use 3 letters here. You're right, they're vertical around here. You said ABC? Wouldn't CF be in the middle? So if I change that, I go angle ACB, what would be the matching letters for the other way? Good. Louder. ECB. And the reason, if you think about it, if you were doing a proof on this, your reason would just be vertical angles. Because the rest of the stuff is technically given to you in the diagram. Those 5 other statements you were able to infer from the diagram because it was marked. It was given. Okay? That's kind of what we're looking at doing here today. As things get progressively crazier, if you will. Right? But is it tough? No, you're just looking at a picture. Oh, speaking of pictures, back on that progression thing real quick. One of the things I would put on there, because I know this shows up a lot, I would draw a picture of a bow tie. Oops. Draw a picture of a bow tie like this. More often than not, that's kind of what the diagrams look like when you deal with triangles that have vertical angles. Some sort of a bow tie. That's usually what it looks like. like that, or sometimes I'll do it like that. So if you turn your head a little bit, it's still a bow tie. Okay. Usually what they look like if you have that. Yeah. But that's usually a dead giveaway that you'll have to do vertical angles. Because that's not something they'll give you, it's something you have to earn for around it. Okay? Just want to make sure you had that. Just maybe put a little picture that says look for a bow tie. Okay? Okay. Please don't die. Which then allows me to look at this. If I look at this congruency statement, it says that triangle ABC is congruent to triangle FED. You okay with that? All right. Now, excuse me. Before I get too far, how many degrees are in a triangle? It's called the triangle sum. The triangle sum means there's always be 180 degrees in a triangle. Obviously, if it's on a flat two-dimensional plane. I showed you guys what happens if it goes three-dimensional. Right? On the sphere. No? No. Yeah, that wasn't it though. If you take a globe, it's close. If I take this is called a sphere. Yes, you okay with that? If you draw from the North Pole, if you will, for lack of better terms, and you draw to the equator, that's a longitude. Longitudes are all perpendicular to the equator, no matter where they're placed. If I draw another one from the North Pole down where it's 90 degrees at the top, that's possible, which makes this another 90 degree angle here at the equator. Which technically means that's a triangle with 3 right angles. So this is completely possible to have triangles with more degrees, but you have to change where the triangle occurs. Yeah, where it's placed. Okay. So obviously this is nothing you guys will ever have to do, but it's not kind of cool. You do non-Euclidean geometry in college. Non-Euclidean geometry in college. It's axiomatic math. It's basically, it's a class of every single theorem that you ever learned in geometry and why it works. But back to this. So you guys all are in agreement that if you follow the letters A, F, B, E, and then C has to be the same as D. It has to be. Now, we knew that these two are 75. What's 75 and 30? 105. So 105 plus something is 180. Okay? Well, let me write this out real quick. And we know that 105 plus F versus D is also 180. Now, if you look at it, you guys are both saying that they're equal to 75. And D. Do these two things equal the same thing? Yes. Which means they're equal to each other. Now, here's the thing. If you know what two angles add up to equal in a triangle, won't the third angles always be the same to each other? Yeah, it always happens. That's called the third angle theorem. If you know two angles in a triangle between two of them, the thirds will always be the same. They have to be. Math's like that. It won't work otherwise. Okay? Not something we use a ton, but a lot of times you'll see it mixed in with some algebra. Ooh, wrong one. Switch between two sets here today. Where's the other one? Okay. Figure out X and Y real quick. Please and thank you. AC has to match up with DF. Okay, well, you have them both. 3x equals 9. What's X? It's really, really nice when you only have one segment on both of them. You do the same thing with the angles. Angle A has to match up with D. Letters. What's Y? 5. Okay. Nothing too crazy. Has to be that you can write up, excuse me, write your lists, follow the pattern, and math is not too bad. Okay. So, that's where I have that. Do these, please. Congruency statements, very simple algebra, nothing too crazy. Okay. Thursday we will revisit this just because I know it's, like I said, the third fun day of the day of the week, and we will go back over all that logic stuff we did. Law of syllogism, detachment, how do you tell between the differences, converse, inverse, contrapositive, P's and Q's, that stuff. And we'll have our quiz then on Friday. And usually that quiz generally doesn't take all that much time, and I was not going to start anything new over a weekend. That's a certain level of meanness that I haven't reached yet. There's still time. Okay. There's still time. Don't forget, screenshot it. It's in the book. Yeah, I think it's 4.1 is technically the chapter. Hey guys, we skipped around just a little bit with some of the sections. This was technically 4.1. Last week we were doing 2.6 or something. So we moved it around a lot.